All right, so a couple of examples on determining whether a given distribution describes a probability distribution. So number one, recall that number one, each value lies between 0 and 1. And number two, or letter B, the sum of all probabilities equals to 1. Okay, if you get something like 1.3, 1.4, no. So that's not a probability distribution. We could add a couple more points here, by the way, like letter C. Let me make some room here too, so I can fit everything here. So let me put it up here, make it smaller perhaps, and no negative probabilities. And that basically comes from here, because the probabilities lie between 0 and 1. All right, letter D. Well, not letter D, never mind. That's enough. So let's determine whether the given examples do we have a probability distribution. So if a person is randomly selected from a certain town, the probability distribution for the number X of siblings is described in the accompanying table. For example, a randomly selected person in a certain town was asked, how many siblings do you have? Well, 0.22 or 0.27 or around 27% say 0, 24% so 27% said 0 siblings, 24% said they had one sibling, 23% two siblings, 10% one sibling, three siblings, 6% four siblings, and 0.03 or 3% had five siblings. Now, in this case, letter A, condition A is met because all P of x's are between 0 and 1. See, all these numbers are between 0 and 1. But in this case, well, letter B is not going to be met because if you add all these numbers, the sum of this equals to 0.73. All right, and the probabilities do not add up to 1. So that's why in this case, this is not a probability distribution. Okay, let's look at another example. In a certain town, 50% of adults have a college degree. From that 50% that represents the population of adults that have a college degree, they sample some randomly selected adults. So let's see. So from this table, let's look at whether this is a probability distribution. So X is the number of adults, and P of X the probability that they have a degree. So for example, what's the probability that when from the sampling, none of them have a degree? Well, that's the probability. What's the probability that out of the sample of 4, they have a degree? Well, it's 0.25. The probability that 2 from the sample have um, a degree, a college degree, and the probability that 3 have a degree, and the probability that 4 have the degree. So in this case, well, let's see if we have a probability distribution. For letter A, well, all of these probabilities are between 0 and 1. So that's met. And letter B, well, let's add all these numbers. If you add all these numbers in the calculator, the sum of them equals 1. All right, they add up to 1. So this is also met. So this is a probability distribution. Okay, let's look at another example. Determine the probability distribution's missing value. So this is a very classical problem in this case, well, so we have a table that describes the probability that a tutor will see either 0 students, 1 student, 2, 3, or 4 students on a typical work day. And well, they're giving us here some value, the probability that the tutor sees 0 students, or see 1 student, 2 students, 3 students, and 4 students. So in this case, what's the value here? What's the missing value? So that this describes probability distribution. Well, you need to recall that the sum of all these values has to be equals to 1. That is 0.38 plus 0.35 plus 0.16 plus 0.08 plus the missing value, which in this case is x, you can call it x, that has to be equal to 1. Okay, that has to be equals to 1. And well, if we combine like terms, that is, add up all these numbers right here, this is going to give us 0.97. So we're going to have x plus 0.97. That equals to 1. And all we need to do here is solve this baby equation for x by subtracting 0.97 on both sides. Cancel, and x equals to 0.03. So this right here has to be 0.03 in order for when we add these 5 numbers, the total sum equals 1, and therefore this describes a probability distribution. Let's look at another example. So a box contains recipes from 5 categories. The following table shows the possible categories and the associated probability for a recipe randomly chosen. What is the probability that as a percent of randomly selecting either an appetizer or a salad category? Round to the nearest tenth of a percent. So in this case, so you might remember we have done problems like this in chapter 4 in probability. However, those problems didn't come from getting the data from a table. You were just given the numbers in words. All right. And if you think about it, well, here we have 2 events combined. One of them is appetizer, the other event is salad. Okay, so let's highlight the corresponding appetizer and its probability, and salad and its probability. So recall that when they ask us to find the probability involving or, all we need to do is add these two. All right, so let's let event A equals appetizer and event B to be salad. Event B is salad. So when we do the or, okay, we're looking for the probability that either A or B, and all we do is add the two probabilities and subtract any overlaps. But in this case, from this table, there's no overlap because this is not a two-way table. So in this case, we can just get rid of that term. We don't need to use it. These events are not these are actually mutually exclusive events, right? Appetizer and salad, well, I mean, in this case, they're not overlapping. So all we do is add these numbers, and so in this case, 0.210 plus 0.173, which adds up to 0.383. And well, in this case, they're asking us to round to the nearest tenth of a percent. So we need to convert this number into a percent like this. So 0.383, that's the same as 38.3%. Okay, that's final answer. A very similar example in this case, well, a summary of types of movies is shown in this table. The following table shows the genres and associated probabilities for that type of movie available on a particular weekend. The table is a probability distribution. How do we know? Because if we add all these numbers, they should add up to 1. Okay, so that's how we know it's a probability distribution. And also, every single individual probability lies between 0 and 1. If we choose a theater and a movie to attend at a random, what probability would we have of seeing anything other, be careful here, anything other than romantic or scientific movie? So we want to watch anything else, not romantic or scientific or science fiction movie. So let's cross out. All we have to do is cross out romantic and science fiction. We don't want to watch that. So we want to watch any of the other ones: drama, adventure, or foreign. All right, and then in this case, if you set up the 3 events, event A, drama, event B, adventure, and event C, foreign. So this is what we do. So let's set up the probability. P, or the probability that either A or B or C, this will be only the sum of the probabilities. I know, in this case, why don't we just add these numbers in the beginning? Yes, of course, but I mean, we need to be very, very detailed when it comes to notation and explain why are we adding, because in this case, we are looking for either one of these, right? And it involves to write the sum of the probabilities. And then if we had overlaps, we would subtract it. But in this case, again, this is not a two-way table. This is just a one-way table. And in this case, we just add individual probabilities. That's 0.302 plus 0.290 plus 0.085. When we combine these together, we should get 0.677. Let me 0.6. Oh, come on, this 6 is not coming right. 77. Well, in this case, they're not asking for the probability as a percent, but if they did, make sure to do 67.7, right? Either way. So depending on the choices or depending on instructions. And one last example. So students at a local middle school were asked how many siblings they had, and the results are shown below. Find the probability of each number of siblings for a randomly selected student in the school and record the results in the table form. Be sure that all the total probabilities is 1. Okay, so in this case, they're not giving us probability. They're asking us to find them first and then construct the probability distribution. Instead, they're giving us the frequencies. What do these frequencies represent? So they're surveying the students at the high school, at the middle school, and asking them how many siblings do they have. 198 students have 0 siblings. 248 students have 1, 131 have 2, etc. Okay, all the way. So yeah, so there's 3 students in the school who have 7 siblings. All right. So now, how are we going to find this frequency? And this is going to take us back to chapter 2. So to find the probability, from the chapter 4 perspective, we need to divide the number of successes per total number of outcomes. So we're going to divide each of this number by the total number of students, and in this case were surveyed, and in this case this is 671. So what do? Divide each number by 671. Okay, and the probability for each. So if we divide 198 by 671, we should get 0.271. Oh, not 271. Give me 1 second. It's 295. 0.370. 0.195. 0.080. 631? No, 0.31. 0.031. 0.015. 0.009, and last but not least 0.004. And if we add all this add up to 1. So that's how we know this is that the table we just constructed represents a probability distribution. Now, I mentioned earlier, how does that take us back to chapter 2? Because this is really the relative frequency It's a relative frequency. But now we give it a different context. We call it probability distribution. All right. So what about all this probability distribution? So, well, this one you don't need to write it, or if you want to write it on the back side of the page. So on this chapter, chapter 5, we we describe probabilities, but in the form of a function. So let's go back a little bit to algebra, in which you learn how to determine whether a given set represents a function. For example, you were given these order pairs right here. You wrote the domain and the range. Okay, so 3, 4, 5 in the bubble notation, 1, 6, 7. And then you use arrows to determine where are they going. So 3 goes to 1, 4 goes to 6, and 5 goes to 7. And in this case, then you say that this was a function. This is a function because none of the elements in the domain go to more than one element in the range. All right, so let's see if this is the same for the second example. So in this case, we have these order pairs. The domain represents the x's, the range represents the y's. And well, in this case, we have for x's 3, 4, and 3, we don't need to repeat the 3, and then 1, 6, 7. So let's use arrows. So the number 3, according to the first order pair, the number 3 goes to 1, the number 4 goes to 6, and 3 goes to 7. Well, in this case, what do we have? 3 is going to two different y values. So one element in the domain is mapping, in other words, or it's going to more than one element in the range. So for this reason, this is not a function. All right. So we did something similar here. So we checked some of these some of the conditions to determine whether this table of values represented a probability distribution. So number one, well, all the probabilities are between 0 and 1, but in this case, this first example failed to be a probability distribution because it failed one of the conditions. And well, going back to the functions, well, if you, depending on on what classes you have taken, or whether you have taken algebra, college algebra, or trigonometry, pre-calculus, you may have seen many kinds of functions, such as linear functions, quadratic functions, cubic, radical functions, trigonometric, exponential and logarithmic, rational functions. Now, for this chapter, we are going to look at probability distribution functions. So the first one that we are doing right now are just like the structure of what probability distribution is, and what it's and what their characteristics are. So for probability distributions, number one, we are essentially grouping them into, or classifying rather, into two groups. Letter A, discrete probability distributions, and letter B, continuous probability distribution. And these are the ones that we are going to cover this semester, such as the binomial distribution, which is the next section, the Poisson distribution, and the multivariate hypergeometric distribution, and the multinomial distribution. We'll figure it out, this one. Maybe we do it, maybe not. So, and then we're going to have the continuous probability distributions, and the most common one is the normal distribution. We're going to use it a lot. Then we're going to use do the uniform distribution, and then other distributions such as the student's t distribution, the chi-square distribution, and one more that I forgot to write down here. the F distribution. And that one we're going to use, so this one, the normal distribution and the student t distribution, we're going to use it for finding confidence intervals or to estimate or estimations, and for basic hypothesis testing. The chi-square distribution, we're going to use it also for hypothesis testing, but this one it's going to be used for independence term and for the goodness of fit test. You later on you'll see what we're talking about. And the F distribution, that's what we're gonna do for the last topic for the semester, and we're gonna use it for analysis of variance, most known as ANOVA. So analysis of variance. So we're gonna do that in the end of the semester. So all right, so this is the end of this video. Let's continue on the other video that you might have been working. Okay.